So, welcome back friends to another lecture on quantum field theory and quantum entanglement. So, we were looking at how to write the interaction theories essentially in the last class. So, we introduced how to introduce interactions. We were looking at free scalar field theory interactions essentially. So, the most general form of the interactions we looked at were essentially things like 5 power n sort of interactions. See, these are the most general interactions you can write down, and then I went on to the process of classifying starting 5 power n interactions either in terms of relevant, irrelevant and marginal operators, because remember that phi is an operator. At the end of the day we are dealing with the operators essentially. So, when phi is an operator, these are you have to call them as relevant operators or marginal operators or irrelevant operators. Then for each case I said I also used words like soft terms and renormable and non-renormable terms. What it means is that when you do higher order perturbation theories, higher order perturbation calculations with this kind of. So, the basic idea here is that whether you can treat this interaction as a perturbation over the H0, okay, whether if we can treat the interaction as a small perturbation on the free field theories essentially, and then whether you can make these answers look what you call physically acceptable or not. This is the main point essentially, that in which case you can make this look physically acceptable. And I said okay, in the case of the lambda phi cube it is a very obviously easy answer, because at high energies it is a very relevant operator and at low energies it is not so much, okay, it becomes large and everything. Whereas the marginal operator is an interesting case to look at essentially, because it is renormable. That means you can make physical results out of it, meaning you can connect it with the physical observables. Whereas the irrelevant operators, couplings which are 5 power 5 or 5 power 6 or so on, so contain couplings which are negative mass dimensions. So, lambda power 6 will contain something like -2 negative mass dimensions, and which we know that it grows exponentially very fast with energy essentially, and it has problems in connecting with the physics essentially at the end of the day with physical reasons. So, due to all these reasons we just focused on lambda 4 theory essentially, which we call as a phi 4 theory. So, phi 4 theory Lagrangian, we have written it and we showed that the number operator is no longer conserved because of the interactions. So, you have particles and which are particle number is no longer conserved. So, then we started looking at what is called the Schrodinger picture and the interaction picture essentially. Then the Schrodinger picture, in which case where the states evolve with time and operators do not evolve, and the other one is the Heisenberg picture, operators evolve in time and states are constant in time. Okay. So, the operators evolve in this particular fashion. You take a Schrodinger operator and sandwich it between e power ht and e power minus ht, where the states evolve with e power h. So, the basic idea is the h here is h0 plus h interaction essentially. So, the point is that h is nothing but the total h is h0 plus h interaction. In the interaction picture, if you want to deal h0 as the Hamiltonian of the free fields and hi as the Hamiltonian of the interaction part of the Lagrangian, and we want to deal hi perturbatively. The basic idea is that hi should be perturbative. So, now we will continue with the formal evolution of this interaction picture. Okay. So, let us continue with the interaction picture. So like I said, the total H is H0 plus Hi. Now the point essentially is in we want to see how it evolves essentially. The entire thing is that H0 is the Hamiltonian of free fields interaction part Li, this already mentioned it, that Hi, that means that the interaction part of the Hamiltonian and Lagrangian are equal to each other. So the basic idea is that so H0 will be governed, H0 governs the operator's time evolution. Let me express it right. Whereas Hi governs the time evolution of states. So in this sense, this becomes the mix up, okay, of both Heisenberg picture and the Schrodinger picture. So that what is the basic idea is that you want to evolve the operators, you want to keep the operators in the Heisenberg picture, but with free Hamiltonian, whereas the states evolve in the Schrodinger picture with the interaction Hamiltonian, essentially with the interaction Hamiltonian. That's the basic idea essentially. Okay, so this entire thing is called the interaction picture, which is a mixture of both Schrodinger picture and Heisenberg picture. So for this we introduce a new new index as psi I. Okay, so psi I so this is just the Schrodinger state moving into the interaction picture, and O interaction is equal to e power I h t over Schrodinger minus I h t. So we can convert operators states from Schrodinger picture to interaction picture by multiplying with e power I h0 t. But this is not the full time evolution of the states. Essentially, we just brought them into the interaction picture. And similarly, the operators into the interaction picture from the Schrodinger picture will move to here essentially with H0. I will just show you what I mean by saying that the states in the interaction picture get evolved only purely in terms of, so psi I of t evolves just in terms of Hi of t essentially. Okay. Okay. So now H int okay will also be the same thing essentially. So now Hi is equal to H int of I is equal to e power I h0 of t H int e power minus h0 of t. So so the free Hamiltonian operators are already from the Schrodinger equation fixed into this, and I define something called Hi also in the interaction picture, which only applies to the interaction part of the Hamiltonian, which is H int, which is equivalent to the Lagrangian interaction part of the Lagrangian essentially, H int essentially. So we can start with the Schrodinger picture. I want you to derive that the statement I made that the states evolve only with the Hi, in the interaction picture. For that I will just write it down as I start with the Schrodinger picture so del by del t I wrote it in terms of h0 plus h plus high h and t. Okay. So this just becomes so this is nothing but hi of t. So this is the first formula I d psi I of t okay. So this is the first formula we have seen that what I did here is it looks a bit formal. I did not do much. I defined how to move from the Schrodinger picture to the interaction picture by this formula. Then I also moved from the interaction picture operators essentially. Then I see that the same thing also applies for H interaction. So similarly H interaction is different from hi. Okay, H interaction in the Schrodinger picture is also the same okay, which is H interaction I. Okay, in the interaction picture H interaction also is modified by e power I 0 with the free fields free Hamiltonian here. So this is important. Using these three I can start with the Schrodinger picture, okay, and simply using these three I can derive del psi I by del t is equal to hi of t. So within the interaction picture one has the thing that the evolution of the operators the states essentially, sorry, not the operators, the evolution of the states only is impacted by hi. Hi is the interaction Hamiltonian in the interaction picture. So this is the interaction Hamiltonian in the interaction picture. Okay. So this hence proves the statement saying that this is what we want. Now we want to solve this. So this is the most important equation. If I know what it is, I have solved this, I have a solution for the interaction picture, how the states evolve essentially. So the solving is you can formally write an equation for the solution, and that formal solution is given by Dyson's formula. Okay, it is given by Dyson's formula. Okay. So the this is slightly formal, but let's go through it. When I have been saying this formal, but anyway, so let's write it down. Essentially, let's see what it means. Essentially, what this formula. It's a very interesting formula and it's very important actually. So we can write this thing psi of t, all interaction picture, is equal to u of t t0 psi of t t0 in interaction picture. So the basic idea is that what I have expressed, this u of this entire solution, the solution e power hi of t essentially is what, that is a basic idea. That now the point is that if h is a constant or anything, I can take this and write it in terms of exponential of h of it. But h of it is a operator. H of it is an operator. Okay, so is an operator. So one cannot write u of t t0 is equal to exponential minus I integral t0 to t hi of t prime dt prime. Now this is a not correct. So this is not correct. Okay. The reason is h is a operator, so it's like a matrix essentially. So you have to work out the entire thing essentially. Okay. So there are a couple of issues now, not completely correct. Let me put this as, now the point is that if you want to write t of t0 is as this, then it's no problem. The point is that because this is an operator, you have couple of subtle points. One is something called the time ordering. When you expand this in terms of a series, you have to always make sure that the previous time comes before the later time. Essentially the previous time should always be coming before the later time. Okay. So so that is called time ordering. Given in this fashion, no time ordering is present. Because you are evolving in time, because it is an operator, it is an exponential, it is a series essentially. So it is a series e power, okay, to make it much more concrete. Now I am expanding the exponential. So you have one, because hi is a small quantity, I am doing perturbation theory here. Okay, I can do expansion of the Hamiltonian in the series essentially t0 to t hi of t prime dt prime whole square. Okay. Now if you differentiate this, okay, let us just differentiate this with respect to time. If you differentiate with time, you get 1 by 2 quadratic term differentiation. So this is the first term in the differentiation. It's a square term, right, essentially. So it's 1 by 2 the first integral and derivative cancel, so that gives me this minus 1 by 2 hi of t integral t0 to t hi of t prime dt prime. Now the point is that if you look at this essentially, so if you see hi of t is sitting on the right here. So this is fine, you can integrate out the t part essentially, and so it sits on the left essentially hi of t, but here hi of t prime, when you integrate it out, it sits on the left essentially. So it sits on the left, so it sits on the we cannot convert it because you can okay. So now this is why this is a problem, because we need it here, I don't know, here. So we see that okay. Okay, once we write it this particular fashion, so we have I du by dt is equal to hi of t u. So you need to satisfy this thing. So you need to satisfy this particular thing. The moment we say that, so if I represent this thing into this, so I can integrate it out, I du by dt is equal to hi of t into u. Okay, this is the the function where u of t t0 is the operator which keeps taking in time essentially, such that u tt is equal to 1. Okay, this operator takes when the time is same essentially, it should not evolve essentially, this is obvious. So there is a state should not evolve when the time is the same, and you also have that if you have multiple slices essentially, these slices should be in such a way that u t1 say t2 into u t2 t3, maybe I will write it down separately. Okay, u t1 t2 times u t2 t3 equivalent to u t1 t3. Okay, so it should so this operator should be adding up essentially, adding up the time intervals in between time intervals. So this is essentially the condition on this operator. So what it means that if you have an intermediate time, if you have any intermediate time, it should fall before the final time. If you have an intermediate time, it should fall before the time and time. Now when you do this integration here, the quadratic term integration, what you see is that this is sitting on the right. Okay, it's sitting, the hi of t is sitting on the right with a t essentially, sitting on the t essentially. This means that once you do this integration, you won't be able to match it with each the u term. If you define the u term to be u of t0 t0, then this sits on the left to the u, to u, sitting on the right here to the u. So it should not, here by definition it should sit on the left of u. Okay, In other words, what it is it doing, it is introducing an intermediate time on the wrong side essentially. That means it is introducing intermediate time beyond the time intervals, essentially beyond the time intervals. So for this, okay, when you are expressing directly as an exponential, like a matrix exponential, and then trying to solve this, you will end up in problems essentially. You will end up in problems because you are not worried about how the time is progressing. Okay, you are not worried about how the time is progressing. So for this, we need to introduce something called time ordering of operators. Okay, so what does time ordering of operators do essentially? So time ordering of any two operators T1, product of two operators T2, gives me O of T1, O of T2 if T1 greater than T2, O of T2 of T1 if T2 greater than. This essentially tells you that the time should be ordered, essentially that time should be ordered. Okay, so the U is now defined as time ordered product of exponential minus I integral T0 to T Hi of T prime dt prime. This is the main thing essentially. Okay, so this capital T is a time ordering. Without the time ordering, you will end up with violations we talked about. Okay, violations of causality. You will end up with all kinds of problems essentially. Okay, expanding this expression, I will just write down the compact form, and that will give you the Dyson's formula. Okay, so let me write it down. Essentially, this is just one step. So just expanding now in terms of the Dyson's formula. U of T0 is equal to 1 minus I. Is the same thing. The first term does not change because it is the same thing as earlier. Hi of T prime plus minus 1 by 2 square. Now because we have the time order product, you see what is happening. T dt prime integral T prime to T T double prime Hi of T double prime Hi of T prime plus T0 of T dt prime T0 of T prime dt double prime Hi of T prime Hi of T double prime. Okay. Now see how we express the second order product. Okay. So one term is Hi of T double prime Hi of T, the other term is Hi of T double prime essentially. Now you see how the indices also modified essentially. So one is T0 to T prime to T. Okay, and my note this should be clear, otherwise you will miss the point. T prime to T Hi of T double prime Hi of T prime. So this is fine, the T prime is on the right. The second integral has a units T0 to T and T0 to T prime. Okay, this is the total integral which Hi of T prime, and now you can express the second integral So the last two terms will double up essentially, and the final formula you can express by just by replacing essentially. Okay, so you can, okay, let me write that step also. So you have T0 to T dt prime, T we have T prime to T. So you can express this entire thing. The last two terms T0 to T is a thing essentially. So T prime, okay, is equal to H I T double prime H I T prime is equal to T0 to T dt double prime integral T0 to T double prime dt prime Hi T double prime Hi of T prime, and this is equivalent to T0 to T dt prime T0 to T prime dt double prime Hi T prime Hi T double prime. So the term we got in the last essentially is T0 to T, T0 to T prime, Hi T double prime, Hi T prime, and that is equivalent to, you can express this again just by variation and express it in this particular fashion, that T0 to T, T double prime, and then H T0 to T. Okay. So this you see is equivalent to the last term essentially. Okay. So remember that the range of integration is always that T double prime is always greater than or equal to T prime. T double prime is always, so it's always time order essentially. And in the second expression is T prime is greater than T double prime. Okay. So this means the final proof is U of T0 T0 is equal to 1 minus I T0 T dt prime Hi of T prime plus minus I T square T0 to T. Notice the intervals essentially T0 to T prime dt double prime Hi of T prime Hi of T double prime. Remember that T double prime is greater than T prime, and so on. So that's it. This simple compact formula was first of course observed by Dirac. Okay. And later put into this compact form by Dyson. This is the Dyson's formula, and now we are I think we can understand the formal interaction picture and how this appears, and then we will start applying for an actual interaction, and we will encounter something called the Wick's theorem in the later series, and you will explicitly see why particle numbers are conserved and particle numbers are violated essentially, in which cases they are conserved and which cases are violated, and then we will start applying it for simple scattering process, and hopefully we will move further to the what do you call fermions and Yukawa theories also. Okay. So I will stop here, and I will see you soon in the next class essentially. Okay. Thank you very much.